All right, so kind of left off introducing the idea of the Bayes theorem. We'll work through some more examples of that today. Then kind of move on to the next topic. In terms of kind of where we're at, just some housekeeping stuff. So I put up two practice exams with their answer keys, along with the formula sheet that's on Canvas under the Files tab. It says something like, exam 1 practice material. So those are all in their own folder. All the slides, skeleton and then complete up to this point are also under the old lectures folder on Canvas. So as we kind of start getting closer to the exam date, which will end up being, as I posted on Canvas and I said in class last week, October 1st, so next Friday. So we'll kind of finish covering material this week, maybe a little bit on Monday, and then kind of part of next Monday's class and Wednesday, we'll basically doing some exam review, going over some of those practice problems. So once you kind of get those two homework assignments out of the way, start looking at those practice exams. If you have any questions next week, then obviously I'll prompt you guys, and we'll start with ones that you have specific questions on. Otherwise, I'll kind of pick and choose the ones I think are probably most beneficial to cover. No questions from me before you just jumping into things today. Okay, so we left off last class talking about Bayes theorem. We had this example where we're talking about HIV positive, HIV negative individuals. The probability is that they see a positive outcome of the test, not necessarily a positive outcome, but if they get a positive, that's what the test says, or if the test says negative. What does that tell us about the conditional probability of, given that we see a positive test result, what's the probability the person actually has the disease? So I'll frame this in a slightly different example today, but it really works the same way. So let's say we've got this scenario, and it's going to be kind of goofy at first. I'll then try to transfer it into a more practical example you can see in real life. So let's say we've got people who are suspects of committing crimes. We take them in. Our society has found this truth serum, and we're okay using it. So this truth serum either makes someone say they're guilty or makes them say they're innocent. And the whole idea is it's a truth serum. Hopefully, it's making them tell the truth. So given that someone is innocent, right, this truth serum accidentally makes the people say they're guilty, right, 1% of the time, or with a probability of 0.01. And then given that they're guilty, this truth serum makes them say they're innocent about 0.1% of the time, or probably 0.1 or 10% of the time, right? So it doesn't always work. So we've got these two conditional probabilities. We can start to think about, okay, what are our states of nature, right? Well, someone is either innocent or they're guilty. So if we're thinking about, well, the first one I have is the truth serum makes them say, and I'm probably just going to use shorthand using G for guilty and I for innocent when I'm writing this on the board in terms of the outcome of the test. So when you think about our state of nature here, is that whether or not someone's innocent or guilty. And then our outcome of the test is that the truth serum makes them say they're guilty. So one thing we talked about last week is if I know this conditional probability, indirectly, I already know another probability as well. Right? So this was the idea that we said, if we conditioned on, well, I'll write this down here, the same state of nature, and we looked at the probability of the other outcome of the test, call that EC, right? Outcome of the test. If I condition on the same state of nature here, that someone is actually, in fact, innocent, what does this probability have to be? Right, so given that someone's innocent, I know the probability that for that innocent person, the truth serum makes them say they're guilty with a probability of 0.01. So the probability that, given that that person's innocent, the probability the truth serum would make them say they're innocent would be, right, just the complement of that, or kind of add up to 1, so 0.99. Now remember, we're living in this world, when we talk about these tests, we're thinking about no inconclusive results, so we only have 2 outcomes. And it's not a far-fetched, even if we think about this truth serum that doesn't, the person says nothing the first time, and we just give it to them again until they either say they're innocent or guilty. So anytime we're given a conditional probability where we're conditioning on the state of nature, if we condition on that same state of nature, look at the different outcome of the test, those will always add up to 1. Now, I didn't build it for you last class. I said so some people might make it make a little more sense, so I'll do it today. But sometimes we could use like this tree, this probability tree. So the other piece of information we didn't have is of all the individuals that are suspects, 5% of them are guilty. Right? So of all the suspects, without any information about their actual guilt or innocence, right? We know that the probability, if I selected one of these suspects at random, the probability they're guilty is 5%. So this is a little bit of kind of a weird one, but we'll think about our two states of nature are that the person is guilty or innocent. We've got kind of our two branches of this tree. We said we know that kind of this, on the same row, those things should have to add up to 1. So the probability that someone's guilty here is told to us to be 5% of the time, so 0.05, which means the probability that they're innocent would be 1. To add up to 1, right? We said these states of natures are essentially like complements. So the probability of an event and its complement always add up to 1. We then said, okay, think about being over here on this branch. I maybe have to write a little small to fit everything on here so you can't read something, make sure you ask it. And we think about on this branch, right? We're going to condition on whatever the state of nature is on this branch. So we're going to have two probabilities over here, but we're conditioning on the same state of nature. So the thing that we're interested in, once we condition on that state of nature, is okay, what's the probability that we see certain outcomes on the test? So either the truth serum makes them say they're guilty, or the truth serum makes them say they're innocent. So given that someone's guilty, the truth serum made them say they're innocent, what? With a probability of 0.10. So this is why the tree kind of helps, kind of lets you see. When I'm conditioning on the same state of nature over on this branch, these two probabilities, I'm looking at the different outcomes of the test, have to add up to 1, right? Given that someone's guilty, this truth serum either makes them say they're guilty or it makes them say they're innocent. Those are the only two things, right? So the probability, if we add those two probabilities together, it has to add up to 1. So this conditional probability should be 1. That's 0.1. So it would just be 0.9. And then this tree is going to look a little weird because I'm otherwise going around the room, but I'm shorthand here, so maybe I can put the other one. I'm not sure I'll be able to. Right? We've got condition on that the person's innocent. Now I can think about, I'm conditioning on the same state of nature here. Truth serum equals I. So now I'm conditioning on my other state of nature, right? The state of nature on this branch, but still looking at the conditional probability for the two outcomes of the test. Well, I have one of these, right? Given that someone's innocent, the truth serum makes them say they're guilty with a probability of 0.01, which then, given that someone's innocent, the truth serum accurately makes them say they're innocent with a probability of, we're on the same branch, right? This is the idea that these have to add up to 1 as well. So if I do it this way, I've got everything I could ever need, right? I may not need all those pieces of information, but I could answer any question now that I'd be asked about this, given these, 6 probabilities? So we got all of our probabilities straight. We can identify what we're given. We actually could find some of those missing pieces potentially. We did that ahead of time, even though we're not sure if we have to do it, depending on what question we're asked. So to define what we're looking for, right, we'll go back to that other slide. I had a question on there. But the general question would be, okay, this truth serum is making people say they're either innocent or guilty. And that's all I see. I don't truly know if someone's innocent or guilty. All I can see is this outcome of the test. And so I might be interested in something like, okay, given what I have, the truth serum makes somebody say they're guilty here. What's the probability they're actually innocent, right? So given that someone confesses to a crime after taking this truth serum, what's the probability that they're actually innocent? Well, this is where we go back, we look at that general form of the equation, right? I think we had it broken down as like, here's the E and here's my S1 that I'm interested in. And then it was just like I had this general form of the equation with E and S1, but I have my own example now, so I'm just going to write it out in the context of my example. Okay. So if I do that, I'm just plugging in basically wherever I see an E, I'll be plugging in what I'm looking for, that someone's innocent. Everywhere in that equation where I see that S1, I'll be plugging in that the truth serum makes them say they're guilty. Now, the general kind of intuition behind what this formula is doing is that top part, right? Think about what we're saying. Look at all the people who confess, right? All the people that the truth serum makes them say they're guilty. Well, there's two types of people in that group. You kind of think about our denominator is all the people, right? Behind probabilities, there's always frequencies. So we can think about this as out of the people who have said they're guilty from this truth serum, what's the probability that they're actually innocent? So like the number of innocent people, divided by the number of people who have said they're guilty with the truth serum. That's kind of that's the probability we're looking for. So the way that we can figure out the number of people who this truth serum is going to make them say they're guilty, we'll have two types, right? People who are actually innocent, right? So people who are actually innocent, the probability that someone's innocent, multiplied by, given that those people are innocent, what's the probability the truth serum accidentally or incorrectly makes them identify as guilty, right? Makes them say they're guilty. So that's that first component of the denominator. Everyone who's innocent, but the truth serum actually makes them say they're guilty. And the second group of people we have who say they're guilty are people who are actually guilty, and the truth serum correctly makes them confess to the crime, makes them say they're guilty. So that's kind of what those two groups represent, right? And then that numerator as well, what state of nature we're interested in? Well, out of all these people that the truth serum makes them say they're guilty, regardless of whether they're innocent or if they're guilty, right? We're just interested in the ones who confess, right? The truth serum makes them say they're guilty, but they're actually innocent. And the way that I wrote this out, really go back to last class, look at the general form of the equation. Like I said, we're just plugging in our events. We're writing it out in the context of our example. Now, at this point, it should be pretty easy because we're just plugging in values, right? What's the probability that somebody's innocent? Have over there 0.95. Given that someone's innocent, what's the probability the truth serum actually makes them say they're guilty? So we look over there, given that they're innocent, probability the truth serum makes them say they're guilty. I think it was is that 0.01? No. And I always said, the easy way to do this is first part of the denominator is always going to be the numerator, right? So we're actually going to be putting in those exact same probabilities. Again, for that first part of the denominator, what's the probability someone's guilty? 0.05. Given that someone's guilty, what's the probability the truth serum makes them say they're guilty? Now, if we hadn't built that tree out, when we look up here, just the probabilities we were given, we don't actually have this conditional probability, right? Given that someone's guilty, we know the probability the truth serum makes them say they're innocent, but we weren't told the probability that, given someone's guilty, the truth serum makes them say they're guilty. But the idea was that we kind of were indirectly doing that, right? And so if we think about the fact that we're conditioning on the same state of nature, the conditional probabilities for the two outcomes of the test have to add to 1. Well, then when we were told that given someone's guilty, the probability the truth serum makes them say they're innocent is 0.1, indirectly we were being told given that they're guilty, then the probability the truth serum makes them say they're guilty would just be 0.9, right? We know that conditioning on that same state of nature, the conditional probability for the two outcomes of the test have to add up to 1. So there we go. So we had that ahead of time, but we didn't have that missing piece. Boxes blew off here, but right, we know that those two conditional probabilities had to add 1. So we know that that was 0.9, right? And now it's just a matter of getting this entered into our calculator. Okay? That shouldn't, at that point, hopefully that's not difficult. Any questions over kind of anything in this process, or what if something looked like this or changed? Okay. So if we plug everything in here, we get about 0.174, right? Which, not great, right? Given that someone, this truth serum makes them say guilty, if we see that as the result, the probability they're innocent is actually about 0.17 or 17% chance. If we jailed people off of this system, right, this truth serum, that would mean that 17% of the people in prison would be actually innocent. That seems a little bit high, right? We probably wouldn't want that as a society. We want to develop a better truth serum, probably something that has, where is it? A little bit lower of a false positive. right? And this was the idea that we can kind of get these somewhat counterintuitive results, or that the outcome of the test doesn't tell us as much about the state of nature, because if one group, right, the probability of being innocent is so much higher than the probability of being guilty, that even if we can really accurately identify all these people who are guilty with the truth serum, even with a relatively low false positive rate, we're going to just end up with a lot of innocent people also confessing to crime, right? This was the idea when we said most people are HIV negative. So even though the false positive is very, very low, like percentage-wise, it ends up being just a lot of people who kind of get this false negative, or false positive, sorry. All right, so this is something we haven't kind of looked at yet, but it works very similar to the rule or the idea that allowed us to build that bottom part of the probability tree. So if I think about instead, given, right, that the truth serum makes someone say they're guilty, what's the probability that they're actually guilty, right? So open this up, give you a little bit of time to work on it. I'll write down the general form of the equation here. This side of the board. Give you a little bit of time to work on it. Okay? So it's same numbers, same setup. We're given the same information. But now we're interested in the probability that given the truth serum makes someone say they're guilty, what's the probability they're actually guilty? Kind of our general form of the equation. Actually. Just a second. That's kind of the general form of the equation that we have. Identify what our state of nature and our E that we're looking for is, write that out in the context of our example, and then kind of plug in those probabilities that we had from our, or that we were given. So give you about three minutes to work on this. Talk to the people around you. Think about what we just did or what I went through on the previous problem, and then we'll kind of come together and talk about it. We'll go about the 5-minute mark, so 30 more seconds. We'll kind of talk about it. All right, so I see a lot of people work on this, so maybe I'll just leave this open and we'll kind of talk through this together. So make this one a little bit easier. So let's just stop and think about what we're looking for to begin with. Right? We wanted that given the truth serum makes them say they're guilty, what's the probability they're actually guilty? So what we could have done is use this general form of the equation, right? Here's our S1, here's our E. Just write this out, but in the context of our example. So everywhere there's an S1, write guilty. Everywhere there's an E, truth serum makes them say they're guilty. And just write this formula out in the context of our example. Now, the only tricky part there is what would our S2 be? Our first state of nature we're looking at is that someone's guilty. The other state of nature would be they're innocent. So once we do that, we could then have everything written out in the context of our example, given the work we've just done, and we have it here, right? How is someone's guilty? Was that 5% or 0.05? Are they innocent? 0.95. They're given these conditional probabilities. Maybe we have to kind of fill in some missing pieces because we were given one conditional probability for an outcome test, but that automatically knew the other probability, the outcome, the other result of the test as well. We can plug everything in and get our answer. Now, if this truth serum is even remotely working, right? Hopefully we think, well, given that the truth serum makes them say they're guilty, I'm looking at someone that is the case, right? I'm told that's true. The probability they're guilty is probably relatively high, right? Probably closer to 1 than 0. So if I'm guessing here, I'm probably guessing A or C. However, we think about what we just did, right? Given that someone confessed that the truth serum made them say they're guilty, the probability they were innocent, I think we found this on the other slide, was 0.176. So here I kind of started this out and probably forgot. They said this problem is something similar to what we were doing to build that tree, but a little bit different. So before we said if we condition on the same state of nature, the probability that the two outcomes of the test have to have 2. Well, think about this. Now what we're looking for is given that the truth serum makes someone say they're guilty, well, what's the probability that they are? Spell here, actually guilty. Well, we've conditioned now on the same state of nature here. You have these. We're conditioning now on the same outcome of the test, right? So it's almost like we've taken all of the suspects, everyone, right? Whether they're guilty, innocent, and we've said, okay, only pull out the people that the truth serum made them say they're guilty. So we now have like a smaller group of people. Of those people, what's the probability that they're guilty? What's the probability they're innocent? Well, those two conditional probabilities, I've kind of redefined the number of possible outcomes. I've taken the whole group and I've limited it just down to the people that the truth serum made them say they're guilty. So those people are either innocent or they're guilty. So these two conditional probabilities, when we condition on the same outcome of the test, these will also add up to 1. Right? Given that someone has said they're guilty, they either actually are or they're innocent. So those two conditional probabilities, conditioning on the same outcome of the test, will also add up to 1. Right? Now we usually aren't given this, right? So we had to calculate one of these first, and then we automatically know what the other one is. So we didn't have to go through and use Bayes' theorem again. Once we had this conditional probability, we automatically knew the other one. That was a little bit tricky. We hadn't really went over that that's the case, but kind of, as long as we're conditioned on the same thing, and there's only 2 other outcomes here, or 2 states of nature, we know those probabilities have to have 1. So right, this is what, 0.824 or 26? No, it's got to be a typo. This should be 24, unless I have. Oh, I see what I did. This was 0.174, making that 0.826. We'll go back to the other slide. Maybe if we go back to the other slide. There you go. Yeah. So it's 0.174 we found before, not 0.176. Right? Any questions on that process? hopefully everybody's answered the accurate question now. I'm now going to close it out. So if you haven't, make sure you get your answer in here. Close it out. Okay. So this might seem like a dumb example, but there's a pretty easy kind of like, we can translate this into a real world problem pretty easily if we just replace truth serum with jury, right? So given that a jury finds somebody guilty, what's the probability that they are actually guilty, right? So, given that the jury found you guilty, that you're in jail, what's the probability you're actually guilty? What's the probability you're actually innocent, right? Hopefully it's a little bit better than this, right? We don't want 17% of people in prison actually innocent. But, we could find these conditional probabilities, like given someone's guilty, what's the probability the jury will find them innocent? We can kind of go back and look at like case reversals, like with DNA evidence, to get some idea about how bad juries are doing, right? How often they're finding someone who's actually guilty, innocent, and letting them go. We can also go back and look, okay, where were cases that in DNA evidence didn't exist? How often were juries getting it wrong in the opposite direction, right? How often were they finding someone who's innocent, guilty, right? So we can actually get kind of close to these probabilities looking at previous data, basically case reversals because of things like DNA evidence and after the fact. We might then want to be interested in something like, given that someone is found guilty by a jury, right, they're in prison, what's the probability they're actually innocent? As a society, I would imagine we want this probability to be relatively low. Right? Well, we write that general form of the equation out in the context of our example, try to get an idea about these conditional probabilities based off of previous court reversal data, case data, cases that are reversed. Right, so I had what, given that someone's guilty, the jury finds them innocent, and then given that someone's innocent, the jury finds them guilty. Right? So we do it. I guess I didn't know this wasn't like as relevant of a thing, but if you haven't watched Making Murder, you're doing yourself a disservice. It's a great Netflix show. We could actually find these probabilities, right? So even though it's a goofy truth serum example, right, replace that with jury, and if we can look at some of that actual case data, we could probably would use Bayes' theorem to find something like this. Okay. Any questions over like Bayes' theorem or kind of these examples before we kind of move to the next topic? All right. So the next kind of, the last thing we'll talk about before the exam, like this week and a little bit of next week, are going to be these random variables. For the exam, and that's why I might skip a few slides because I know that on the exam, we're not going to do anything with continuous variables yet, just discrete. Okay? So when we think about a random variable, this is basically kind of similar to the idea of what we've been talking about, where there's an experiment with outcomes, right? But it's just going to be that as we run this experiment and see these outcomes, we record them, right? And then kind of get an idea about the probability of seeing different outcomes. So the random variable is just going to be some experiment that has a numerical outcome that we're going to be recording, right? So this could be as simple as I'm asking with a survey the number of people in this household, right? And then I record, oh, there's 3, there's 7, there's 4, there's 1, right? It's something we just haven't realized yet. We don't know the answer until we actually ask the question or run the experiment. So we've got discrete and continuous. I said we're just going to focus on discrete before the exam. The way that we'll kind of notate these random variables is we'll just write them as a large capital X. Okay? So maybe it's the number of people in the household. We'll represent it with this large X. And then all the different outcomes we see, X1, X2, X3, these are going to be the different values that that variable could take on. If I ask someone the number of people in their household, I don't know the answer, right? But I know the very first outcome might be 0, 0. First outcome might be 1. Second outcome might be 2, 3, 4, 5, up to, whatever the largest household size is. Okay. So with these discrete random variables, typically we're going to have a much smaller number of responses. This makes our life a little bit easier early on. Once we work to continuous random variables, it gets harder, right? But for now, usually a pretty small number of finite responses. We can't see things in between the integers, right? We can see integer values, but we can't see like 6.419. Okay? We've already looked at this slide pretty much before in the sense that I've shown you the number you'll find. It's really the same thing when we were talking about discrete variables before. It's just now they're discrete random variables because Well, not every outcome is equally as likely. It's more likely I get a response of 2 or 3 for the number of people in the household than I get 13. So the number of days you do something is a good example that we had of that. I'm going to skip this continuous random variable because, like I said, I know we're not going to get there before the exam. But some examples like this family size, or the number of dependents on a tax return, that would be discrete. Distance, continuous, right? We can measure distance down to whatever that's what we want. But then I also wanted to bring up, there's something we can kind of do that's unique. Like we almost skipped qualitative random variables. Well, we're not really skipping them, right? If we had a qualitative variable, we can essentially turn it into a discrete variable. So let's say I ask someone like, how many pets they have, what kind of pets they have. Well, they either say they don't have a pet, a dog, or dogs only, a cat, or cats only, or they have both cats and dogs. So those are qualitative responses, but I can use a numerical indicator for each one of those. So instead of writing down they own no pet, I would just put down a 1 for their response. I then know that for this random variable, 1 represents no pets, 2 represents they only have dogs, 3 represents they only have cats, so on and so forth. So I can essentially turn a qualitative variable into a discrete random variable. Okay? So we'll say this one is discrete. I can turn it into kind of only seeing these 4 responses. Any questions over this? This shouldn't be too bad yet. Okay, so we talked about a lot of this. In fact, the rest of today's class, the things we're going to do should look very similar to things we've already done, like 1-to-1. So we've got this random variable, right? And just like when we had a recorded variable, right, in a data set, we could build a frequency distribution. Right? That was what we did in that first Excel assignment. And we've done some of that in class right now. For a random variable, we can come up with a distribution not of the realized outcomes, but a probability distribution, right? The probability when we run this experiment that we see these different responses, right? And every possible numerical value might have a different probability. So we can do the same thing with this probability distribution that we did with frequency distribution. We can put it in tables, graphs. We'll see, probably not today, but Wednesday, we'll start talking about some of these discrete random variables have actual functions that will tell me the probability. So this function we're going to call the probability mass function. Right? This probability mass function for this random variable x will tell me the probability of seeing different outcomes. So typically, this is how this is going to look. I would say something like, what's the probability that random variable x is equal to 2? Right? And then, we'll either have a function or we'll just be told what that probability is. And we'll see some examples of that in a second. So for every possible outcome for x, right, it has an associated probability with seeing that value for x. So every outcome for this random variable x has like a y value, right? It's probability of occurrence. Well, if we have these pairs of values, you can imagine. I could look at something like the number of people in a household, and I could say, okay, the first possible response is 1. The probability it occurs is, I don't know, 0.15. The next possible outcome is that there's 2 people in the household. Maybe it has a probability of occurring of 0.2, right? I could graph these out using these as my x and y coordinates. This probability, right, has to meet all the same criteria as what we had before. The lowest it could ever be is 0. The highest it could ever be, not an interesting example, but would be 1. Right? So more than likely, it's going to be somewhere in that range. Right? For every outcome for x, we know that the probability is going to be somewhere between 0 and 1. And then just like when we did those frequency distributions, we said, okay, if I look at every possible outcome I could see in the data set, and I take the relative frequency of seeing that outcome, we said the relative frequencies always have to add up to 1. Well, those relative frequencies essentially were just telling us the probability that if I selected a data point at random from my data set in one observation, it was telling me the probability that I saw that specific response. It's the same idea here. It's just now I've got all these different x outcomes, right, for this random variable. And I know the probability of seeing each one of those outcomes. So if I add up those probabilities of every possible outcome, those probabilities should always add up to 1. Now, if I take the probability that if I ask someone the number of people in their household, the probability that it's 1 plus the probability it's 2 plus the probability it's 3, all the way up to whatever the largest family is, Well, that covers every possible outcome. Those probabilities should always add up to 1. And that's just the same idea as what we're doing with like the experimental outcome space, right? Almost you can think about this as like a Venn diagram if you really wanted to, right? We're just looking at every possible outcome. When we add all those up, it should cover the entire experimental outcome space. And it gets a little bit easier because with these discrete random variables, we can only see one out. Like if I ask someone the number of people in the household, there's either exactly 2, or there's exactly 4, or there's exactly 1. There's no, these are mutually exclusive responses, right? If I start to think about like it's cumulative, well, then all bets are off. But in terms of the actual response, I'm only getting one response. So anytime I'm looking for the probability of like an intersection of events, I said, well, if they're mutually exclusive, this is essentially 0. So when I'm looking up the union of these events, we said that simply becomes add the probabilities of the events themselves, right? Because usually we have to subtract out the intersection, but there is no intersection. So life's a little bit easier. We'll kind of use something we talked before. So we then move to think about cumulative probability mass function. This works exactly like when we were doing cumulative relative frequencies, right? So it's the exact same idea, right? And because these are mutually exclusive outcomes, it makes our life, you kind of think about this in a different way, and it makes our life pretty easy. So let's say I wanted the probability x is less than or equal to 2. I'm going to keep using this number of people in a household. So that's my idea of cumulative, right? From this value all the way down to the lowest possible, right? That was the cumulative GPA to take this semester all the way back to the very first semester. Well, I want the probability x is less than or equal to 2. That's essentially saying what's the probability x is 2 or 1. So I'm looking for a union. Well, I just said, if I want to find a union, I add the probability of each event and I subtract the intersection. But these are all mutually exclusive outcomes. So there is no intersection. So for this cumulative mass function, all you're really doing is taking the probability that x is equal to 2, whatever value you're interested in, and then adding up the probability x is equal to any value below it, right? Well, in this example, 1's the lowest possible response we receive the number of people in a household. So probably x is less than or equal to 2 is just probably x is equal to 2, plus the probability x is equal to 1. If this was, probably x is less than or equal to 4, that would be the probability x is equal to 4, plus the probability x is equal to 3, plus 2, plus 1. Any questions on this idea of cumulative? Now, we sometimes have a function for this. Sometimes it's a little bit less functional form, and we'll get some examples like that today. But the idea of this cumulative mass function, or what the value, the probability x is less than or equal to a certain value, as I get to really, really high x values, that cumulative mass function gets really close to 1, right? If I say, what's the probability that the number of people in a household is less than or equal to 20? Well, I got to imagine that's got to be pretty close to 1, right? But if I say, what's the probability that x is less than or equal to 1? That's probably going to be quite a bit closer to 0, right? There's a lot of other responses I could see that are above that value of 1. So, whoops, as we approach really small values, right, that cumulative mass function gets closer to 0. So let's look at some actual examples of some data of this, and then we'll kind of work through a few examples together. So I have the misfortune of being a pretty football fan. So I went out and grabbed the last 35 years of data. I think I'm missing the last couple of years now, but and I looked at the frequency for the different number of, I think I had, right, like changes. Sorry, I used to do pretty football data, and I switched it because I don't think all in like sports things. So I did the number of new hires, right? So I went back and looked at some data. You can look at like one specific company and say, okay, every year, right, is a pretty prosperous company. There's been 2 years where they only hire one person, 1 year where they hire 2 people, 7 years where they hire 3, 7 years where they hire 4, right? Kind of the frequency of the number of hires they've had each year over the last 35 years. You're then going to use this data, kind of historical data, to make projections or the probabilities of seeing different numbers of hires in the future. Okay? Well, if I've got frequencies, how can I turn these into probabilities? Simply take the frequencies and divide them by total number of observations, the total number of kind of some of the frequencies here. That's the same thing we were doing with relative frequencies, right? determine frequencies and the relative frequencies, we divide by the total number of observations, right? Well, here, I'm going to do the same thing, right? It's just now that those relative frequencies represent projections for the future, so we're going to call them probabilities, right? Because we're trying to make projections about what outcome we're going to see in the future. So pretty easy to turn these into probabilities, right? We could then graph those, right? I kind of already showed you on the board, and the idea of this, just take the different outcomes, use the probability as the Y value, we kind of make this bar chart, we can kind of see then, you know, usually this company hires 4, 3, 5 people, sometimes a few higher. They never really hit double digits, right? Those probabilities are 0 from the historical data. It's the same thing we were doing with relative frequencies, so nothing really new here. So then this is where it's going to be just like what we were doing before, but actually a little bit easier. Okay. So if I wanted to find the mean of this discrete random variable, right, and I have all these different outcomes for X and their associated probabilities, well, I don't just want to add up all the X values and divide by the number of values I have, right? Because some of these outcomes are way more likely than others. Right? So what's maybe something I could do to find the mean of this random variable? Something we've kind of already done. If certain outcomes are more or less likely, I might want to weight them. So instead of a mean, I might want to find a weighted mean, right? So I'm going to use the idea of a weighted mean. And if I remember what my weighted mean equation was, it was like take my frequency or my weight, multiply by the X value, and then divide by the sum of my frequencies. Well, here instead of frequencies, we've got these probabilities. Okay? So when we think about the mean of a discrete random variable, another term that we're going to use for it, because it's making a projection for the future, we don't actually call it a weighted mean, because that implies that it's already been realized, we've seen the reported data. This is going to be an expected value. Okay? So you might have, if you've had finance courses and things like that, you've probably done this with like a very small number of responses. But you can do it with any number of responses as long as there's probabilities associated with them. So when we think about our probabilities or weights, right? We're taking, okay, the X values multiplied by the probability X's equal to that value. And then I said, if this was a weighted mean, we divide by the sum of the weights, or our probabilities are the weights. But what will the sum of the probabilities across every outcome, right? What will that sum always be? If I take the probability of every possible outcome and add them up, that should always be equal to 1. So I can essentially ignore that denominator. Dividing something by 1 doesn't change anything. That's why to find that expected value of the mean of a discrete random variable, it's almost a little bit easier than finding a weighted mean, right? Because we're using probabilities as our weights, we know that some of our weights are always equal to 1, so we essentially just have that numerator of our weighted mean equation. Okay? Questions on that? Okay. So if I wanted to do this with a small data set, right? All I would do is go through every single possible X value, multiply it by the weight. So 0 times 0 plus 1 times 0.06 plus 2 times 0.03, so on and so forth, all the way down to the very last observation, right? So quite a bit of few outcomes here, so a little bit of work, a little bit lengthy here. But a small number of observations would be a little bit easier. How to end that thing? Skip that. We're going to work through this. I'll have you guys finish this example, then we'll talk about it to end class. So with this idea in mind, that the mean or the expected value of this discrete random variable is essentially just a weighted mean. Let's say X outcome, so the variable I'm interested in, is the bonus that someone's going to get. So this is in millions. You don't have to add all the zeros on to do this. Whatever your answer is, finally, just like an M on the end. So if you could see that there's this crazy investment capital firm, we got the bonus amount to be 10, 6, 3 million, or 0. Now, each one of those outcomes has a different probability associated with it. What's the expected value of this bonus? Right? We'll give you guys a couple minutes. You don't have to be super quiet. Work with the people around you. And the quicker you guys come up with an answer and feel confident about it, and I see a bunch of responses, then the quicker you can do that. I'll give you a couple minutes to work on that, kind of talk about it, and finish out the class. go for about another 30 seconds. I'm gonna close it out and we'll talk about it here and wrap things up. All right, if you haven't taken or put an answer in, take your best guess. We had 31 earlier, so make sure you're getting an answer in. All right, we'll close it out. So if we're just thinking about this one, which of the, I mean, before I even try to plug any values in my calculator, which of these don't really make a lot of sense given what this data is? 250,000 for sure. What would have to be different about these probabilities for our expected value or our weighted mean 250,000? Yeah, it should be, because the only way we're going to get something that's under 1 million is if the probability of seeing 0 is really high. Well, the probability of seeing 0 here is 0.2, right? It's not even the most, it's not even the second most likely outcome. So these probabilities, remember, are our weights. It's what's going to be influencing that weighted mean or that expected value the most. The values that are going to influence that expected value the most are 3 and 6 million. So if I'm taking a guess, I'm thinking it's probably somewhere between those two values that are influencing it the most, right? So if I was guessing, I'm probably going to guess either C or D, right? That, I mean, just looking at the probabilities and thinking about what we're doing, the expected value is probably somewhere in that range of 3 to 6 million. I don't know, which of these makes more sense for putting it in, but the process I'll use, right, is go through every X value, 10, 0.15, plus 6 times 0.25, plus 3 times 0.4, plus 0 times 0.2. If I do that, I end up getting that 4.2. Okay? So, like I said, it's like the way to me, it's like something we've already done, but honestly, just a little bit easy. You don't have to worry about that denominator now at all. Okay? And it's pretty easy to identify our weights because we're only looking at probabilities, right? So that probability will always be your weight. Okay? So we'll talk about the weighted variance at the beginning of next class. We'll transition to binomial distribution examples. I might put up a little video on binomial stuff, but I won't expect that you'll watch it. I've got one that I'm kind of saving for Thursday that I will expect you to watch. We'll kind of start on that next class. I will see you guys on Wednesday.